assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
So for part A, we know that the rotational inertia of the hoop is going to be equal to mr squared. And the energy of the system, E, becomes equal to 1/2 times the moment of inertia times the angular frequency squared plus 1/2 times the spring constant times the displacement squared. We're going to say that here R is going to be equal, rather, R times omega is equaling V, the linear speed, where V is equaling the first derivative of the displacement. And so now the energy becomes essentially E equaling 1/2 times mr squared multiplied by V over R quantity squared plus 1/2 kx squared. This essentially looks like the energy of a simple harmonic oscillator if we identify the mass in the section with the term mr squared divided by r squared. So here, essentially, we're going to say that the mass is equaling mr squared divided by r squared, and we can use then equation 1512, which is now giving us omega equaling the square root of the spring constant divided by, again, mr squared divided by r squared. This is giving us r over r multiplied by the square root of k divided by the mass m. And this would be essentially our equation for the angular frequency. For part B, now, if r is equaling r, then the answer from part A reduces omega is now equaling, this would be r equaling r, this term would become 1. So it would simply be the square root of the spring constant divided by the mass m. And here, for part C, if r is equaling 0, well then the entire term becomes 0. We can then say that the angular velocity then becomes 0. That is the end of the solution. Thank you for watching.